Okay, thank you. I'm Braney Bramham, and I'm in symplectic geometry. And so today I'd like to talk about, to explain what I do with, I'm trying to do with area-preserving disk maps using symplectic geometry techniques. I'd like to sort of go back a bit and mention two older theorems, the Poincare-Birkhoff fixed point theorem and a theorem of John Frank's from like 15, 20 years ago, and then explain a new tool that, one of these theorems is sort of maybe has elementary proofs, even if ingenious. The other theorem has relies on very deep results, and yet this new tool proves both in sort of a relatively sort of similar fashion. So that's sort of the outline of what I'm going to try and do in the next 15 minutes. So I'm going to look at area-preserving disk maps. So my cat unfortunately looks a bit like a devil, but no, sorry. So presumably the area of this is supposed to be preserved under F. And then why would anyone be interested in these? Well, back in the late 1800s, I guess Poincare, amongst others, was trying to understand the three-body problem, which is where you have three celestial bodies acting, influencing each other under Newton's laws of gravity. And he was examining a restricted case where you have all three bodies lying just in a plane. And certain other restrictions, for example, maybe one of them, the one that you're really interested in, has a zero mass and things like that. And then he reduced the dynamics of this to an area-preserving map on an annulus. And I'm going to be looking at disks, which I guess is an annulus with a point removed, at least topologically, just because the tools I have at the moment are more easily applicable immediately to a disk. So the other thing, another reason, he showed this, and that you can view this as in terms of an area-preserving map on a surface, and yet this theorem, this situation from over 100 years ago is still far from being understood. And he also observed that the dynamics are actually extremely rich. So this picture is supposed to illustrate what might happen if you took a computer simulation where you took your sort of generic area-preserving map on this disk, and you studied what happened to a single point in forward time. And so these circles here, for example, is supposed to represent an invariant circle, maybe with some sort of rotation number. And it turns out that generically you'd expect a lot of things like this to appear, where you have these kind of island chains surrounding ones. And maybe even chaos here, like orbits whose closure fills up a set of positive measure. Another thing people have observed in computer simulations is that it looks plausible that when you zoom in on a point like this one here and blow it up, maybe you get the same picture again, and so on. And so maybe it displays self-similarity on all levels. And so there's sort of many striking phenomena you can observe, but maybe little of it is proven. I mean, there are also very successful theories like Aubrey matter theory and so on, deals with certain cases. But in general, there's an awful lot to be understood. Another way in which area-preserving maps come up is studying, if you want to, the history of understanding when there are closed geodesics on a sphere. So this egg is supposed to be actually a two-dimensional sphere with a smooth Riemannian metric on it. And under certain conditions, Birkhoff showed, so back in the 20s or 30s, that you can, in many cases, understand the dynamics of when there are closed geodesics by an area-preserving map on an annulus. So here, if we have a closed geodesic you start off with, and you pick a point on it in a direction, and you follow the geodesic that flows from there until you hit the red one the second time, this gives you a map from the first arrow A to B, and this you can represent by a map on a surface, on an annulus. So, and this turns out to preserve a volume element in a natural way. So this is another reason that understanding this was important. So So Poincaré, looking at the restricted three-body problem, came up with a conjecture, which was, you probably all heard of it maybe, that if you have a so-called twist map, then there are two other fixed points. So he stated it in terms of annuli, but in terms of a disk, you'd say, supposing there's a fixed point here at the origin, and supposing the behavior of the map on this disk is such that near the origin, the points are going around following the blue line clockwise, and on the boundary you're going anti-clockwise, and you can make this rigorous. And then the conjecture he made was that there should be two other fixed points, maybe those red guys out in the middle there. And he died before he could prove this, and then Birkhoff shortly afterwards proved this. And then he used this to understand the closed geodesics on the sphere, and said, well, if the annulus map I get describing this happens to be a so-called twist map like this, then I get two fixed points, and applying it to iterates, I can get infinitely many periodic orbits, and that's what closed geodesics are, and that's what people were trying to understand. On the other hand, if the map you get is not a twist, then what do you do? And it wasn't until there was a breakthrough in the early 90s when John Franks proved the following, which is, so one way of stating this, again he stated it for the annulus, is as follows, is that for a disk, two fixed points implies infinitely many periodic points in the interior. So just to compare again with what you get from the Poincaré-Birkhoff theorem, is that one fixed point you only need, but with a twist condition, also implies infinitely many. And it turns out that the one from Franks resolved all the situations that no one could prove, and completed the story to show that this two-sphere with a smoother Riemannian metric always has infinitely many distinct closed geodesics. And this theorem, in contrast, by Franks, is definitely relies on some very deep theorems. So I'm now going to explain briefly a new tool. So, and then show how to prove, sort of a sketch of proof of the Poincaré-Birkhoff fixed point theorem. So, consider your map on the disk. It's maybe it's area preserving and smooth. I'm missing out all the details here. And then I'm going to represent it as the first return map on a torus, a solid torus. So undo what Poincaré did. So it means we take a flow on this solid torus. There's a preferred disk slice, and if I start at a point on here and follow the flow that I've picked, then you come back to what should be. You've chosen it so that you get the map D. And then it'll be useful to draw this opened out. So here's the solid torus opened out as a solid cylinder with a flow on it, also representing the map. So the tool, I will say, is a global system of surfaces of section. This terminology comes from work of Hoffer, Wazowski, and Zehnder that I'll mention again in a minute. So what is this? So a picture maybe explains much better. So here is this is supposed to be the solid torus opened out to a solid cylinder, and it's got a flow on it that I haven't drawn. And then this object here is supposed to be a singular foliation, where all the non-singular leaves are embedded annuli, because the opposite, the left and right disks are identified by the identity map. And the behavior of this, let me just open it out. So sort of the skeleton is that there's a collection of periodic orbits of the flow. These two I've drawn as straight lines, but really they should be wiggly. You know. And then there are two kinds of leaves appearing in this object. So one is going to be like this, where it's an annulus, because both left and right ends are identified. And the boundary of this annulus lies on two periodic orbits. The other kind of leaf that appears is one that connects a periodic orbit to the boundary. And then you have this sort of picture filling up the whole thing, the whole space. And then what else? So how is this related to the flow? How is this going to tell us anything about the dynamics? Well, not only are the boundaries of these leaves actually sitting on periodic orbits, but the interiors are also, the flow is transverse to them. So if I open this out, this leaf, for example, there, the red arrows are supposed to represent the vector field whose flow takes you, if I start on the left disk and flow to the right, I get the map I'm interested in. And so here you have sort of infinitely many Poincare sections. Of course, each doesn't necessarily give you a return map, but so yes, so they're transverse to the flow on the interior, and on the boundary is tangent. You've got periodic orbits. And a transverse slice maybe looks like this. So this is, take this picture and look at it from a side-on, from a transverse slice point of view. And then this is maybe a sort of picture that you might get where the black dots are a sub-collection possibly of the fixed points of the disk map. And these other arcs are things which are, of course, just a cross-section of these leaves, and you sort of intuitively think of as being transverse to the map. I mean, of course, there's another dimension here that we can't see. In this picture, the graph is kind of tree-like, but it turns out you can also get sort of actual topology here amongst the leaves. And this occurs, for example, here you see the center fixed point is cut off from the boundary. And this occurs when, for example, it's a twist. I'll explain more in a second. And then the bottom one here is what you would get if, for example, the disk map was just something simple like an irrational rotation. So where did this notion of global system of surfaces and sections come from? So this is all work of throughout the 90s by Helmut Hofer, Chris Zosky, and Eduard Zehnder. They built up a whole theory for examining so-called Reeb flows on three manifolds. And a Reeb flow is like a sort of special kind of Hamiltonian flow. And one thing they did that was remarkable was to construct the same kind of object we've just been describing if you replace the solid torus with a three-sphere. And they were able to say very interesting things about certain flows on the three-sphere. And then I copied this approach on the solid torus to get the picture we saw before. And one of the nice things you can do here is that, of course, you can examine, I mean, the solid torus has many lifts, unlike the sphere. And so you can examine different iterates and relate foliations for different iterates of the map to each other and try and glean information from this. So what can we do with these objects, these foliations I described? So let me explain how you can prove the theorem of Poincare and Birkhoff. So recall that this said if you had a fixed point at the origin of the disk and you have this sort of twist condition, then there should be two more fixed points. So suppose you can construct a foliation for, I mean, this is just a transverse slice, but for a whole mapping torus representing this, what might it look like if it contains the twist orbit? So locally near, this is the twist orbit in the center here. Locally, you know that the foliation is going to look sort of like this. And near the boundary, it's going to look like that. And yet the flow is going to be transverse in opposite directions. So, and yet also the flow has to be transverse to the leaves globally. So somehow you can't have this picture where there's a leaf connecting the central fixed point to the boundary, because then some point the map has to be tangent to the leaves and you have a contradiction. So somehow you can't have leaves connecting the central fixed point to the boundary. So you've got to have some topology in your foliation, maybe a leaf like this that cuts off, like in that picture there, that cuts off the twist fixed point from the boundary. And if you have that, you immediately have at least one more fixed point, because you've got this guy sitting out here. And then you just have to say, well, I just need to have a second one, and how do I get a second one besides this one is, well, if you only had one like this, then, well, you've now got a leaf, this ring, where again the flow, I mean, it's always slightly misleading because I'm always taking a transverse slice, but you can make this work. That the flow representing the disk map is transverse to all the leaves, so maybe this leaf here it's transverse outwards or inwards. Either way, you're going to contradict the area preservation of the disk map. So you must conclude that you have something like this. There's got to be an even number of points on, well, actually, let me withdraw that, but you've got to have at least 2 points on this ring appearing in your foliation, so you have your 2 fixed points. Yeah, and so maybe one thing I'll just say as well is that, so you only get these for when for a generic disk map. If you want to take a limit to get degenerate cases, you could have these 2 points collapsing onto each other, and then a priori all you get in the limit is some sort of, well, you only get one fixed point. Where's you going to get the second one from? And this green closed curve is a priori just an invariant set. But it turns out, if you use the PDEs that the leaves are coming from, that you actually get a whole ring of fixed points in the limit if this happens, which are separating the interior twist point from the boundary. So, so in particular, you get 2. So anyway, so the punchline or nice thing about this is that we've used machinery to prove something that can be done in 2 pages by ingenious ways. Can similarly prove this theorem of Frank's. So that's quite nice. And where does all this come from in my last seconds? So this, a leaf like this comes from, in the mapping torus, this picture, which comes from the projection of a cylinder, which is a holomorphic curve. So the picture is this. On the left, you've got a cylinder. This satisfies a PDE. And in particular, it's a pseudo-holomorphic in something called the symplectization of this solid torus. And the fact that it solves this PDE tells you that it, and some finite energy condition, that it goes to connects periodic orbits. And it tells you that when you go project down to this picture we had in 3 dimensions, it translates into the fact that the flow is transverse on the interior. And yeah, I'll stop there, I think. Thank you.